Hello, everyone. This is Matt Yost from GLCom. Welcome, everyone. We're doing another webinar. This is the August edition of our webinars. Um, we try to do one every month on different topics here at GL. Some of them are directly related to our products that we sell and market. Some of them are related to the technologies sort of surrounding our products. So we're excited to do another one here in August. This one actually is a continuation of the one we did in July. So the topic of this one is called WAN impairment simulations for TDM and analog networks. The one we did in July was WAN impairment simulation for packet networks. So that one was very extensive, and we have that recorded on our website. If you're interested in that one, you can always go back and take a look at it. So my name again is Matt Yost. I'm joined by Vijay Kulkarni, who will be our expert today and will be doing the majority of the presentation. Also joining us is Sanjeev Kulkarni, who is going to be monitoring questions that you may have, and if you have any throughout, I just would ask you to either type them into your chat window, which we'll be monitoring, Sanjeev will be monitoring, and then we'll have a session at the end, possibly even in the middle, depending on the time, where we can address some of those questions. And in fact, at the end of the presentation, we may even allow to unmute your own mic, and you can ask the questions directly to us, and we can have a small discussion. So there's a lot to cover today. Again, we're talking about TDM related WAN impairment simulations. We'll jump right in here. One additional note that, as I said before, all of these webinars are getting recorded, so they will be posted on our website if you want to come back to it and take a look at it. Just real quickly here on an overview of GL Communications before we start. I do this every time just in case someone is not familiar with who GL is. But we're located in the United States in Gaithersburg, Maryland. We were founded back in 1986, where we started with doing a lot of engineering consulting services work for local state governments and private cell carriers throughout the country of the U.S. We jumped into test and measurement equipment, so now we offer products in the telecommunications test and measurement world. Those products span all of telecommunications testing, so we offer things in the wireless world, the traditional TDM analog world, voice over IP, IP data, SONET, high-speed things, and so forth. We kind of specialize in PC-based test equipment. Okay, go ahead here. So today we're going to again talk about emulators and WAN impairment emulators. So question would be, why is network impairment emulation important to you? So to simulate network impairments, one as a tester, as a person responsible for a network, needs to be able to characterize how their voice, their data, their video reacts in those environments as they're being transported through the network. So these products that we have and this topic that we're going to talk about today is a way to, in your lab, create this WAN impairment environment. Okay, so we're going to be able to degrade the signal, insert bit errors, insert latency, jitter, and synchronization errors on the network, on the TDM, on the analog network here. So we have the ability through our products, through our software, to precisely do these things and to simulate real-world environments. And that's what you would want to do as a tester, as a developer, is to try to simulate, characterize real-world environments. So we have, again, why is that important? Well, you're going to want to simulate a traffic load in your network. Okay, so we have the ability to do that. We can dial up some different impairments to try to create this environment of traffic load in your network and see how your applications, how your services, how your service level agreements hold up under these conditions. So it's very important to simulate these things in the lab, in your test lab, with your development team, and so forth. And GL has these products, again, in the IP space, which we talked about in July, but now the focus will be on the TDM space and TDM analog areas. Okay, let's go ahead. So again, just a quick agenda, topics covered today, two big categories, TDM impairments and analog impairments. Both we're going to do a little theory, and then we're going to talk about real world, the practice and the real world environment here. Under TDM impairments, the media is going to be satellite, microwave, copper, and fiber. We're going to talk about a lot of different interfaces ranging from datacom, RS-232, etc., to T1 and E1 to higher speed things as we go up to OC12 and so forth. Impairments, as I mentioned before, bit and burst errors. We're going to be able to show you how to inject delay in the network, jitter, which is a function of delay, a varying function of delay, alarms, timing variations, and all of those sort of timing related problems that can happen. Similar on the analog side, interfaces there include 2-wire, 4-wire, and some digital interfaces. Impairments, again, similar, but signal or noise problems in the analog world. Delay, again, obviously a function or is a problem in all of these networks. Attenuation, so the level situations dropping and so forth. Phase distortion, we'll talk about a little bit. And echo, of course, is a big issue here, impulse noise. So these are our topics. These are what the agenda is today. I'm going to turn over the presentation now to my colleague, Vijay Kulkarni, who is our expert in this area, and will be able to walk us through all of these things. So Vijay, go ahead, take over.
Okay. Thank you, Matt. Appreciate it. Okay. Wouldn't call myself an expert, but I'll try to do my best. Okay, so let's back up just a little bit here and just talk about what networks are all about. Why are there networks? If you look at the broad view, ever since man has been, learned to talk, he's wanted to communicate over distances between himself and others, as well as other groups of people afar. So that happened about a couple of 100,000 years ago. And since then, we've been communicating over greater and greater distances with greater speeds, whether it was like smoke signals with Native American Indians or, drummers in Africa, or symbols in caves, or stone tablets, or et cetera. These are all progressions in communications. And obviously, recently, we've been able to communicate with paper. Okay, we had Pony Express, postal system, and in the last century, we had telegraph, essentially the first form of digital communication, and followed very quickly with telephone, radio, right? Data communications, TV communications, broadcast communications. So we've come quite far, and in all of these cases, as we've made progress, what we're wanting to transmit is information, and that information is in the form of voice, video, bits. When, as people learned how to identify information with symbols and bits, image. We want to send faxes and things of that nature, and some of these signals are inherently analog signals, right? Many of them are just at the source. They are analog signals, and to transport them, you have to convert those analog signals in some fashion to be able to transport them over large distances. and that's where the majority of the progress in technology has taken place. At some point in time, people learned that analog signals have a limited amount of information. Although they're continuous, they have a limited amount of information in them because they're restricted in terms of bandwidth, and they're also restricted in terms of there's a lot of redundancy. For example, voice communications has quite a bit of redundancy in it in terms of the frequency extent of it, as well as the amount of information that's carried using analog signals. So they were able to take those analog signals and be able to convert them to digital. When you do that, of course, you do lose a little bit of information because you have to describe that conversion process. You have to somehow pick a conversion process. Like, for example, you have to pick the number of bits to sample, the number of bits used in the sample, 8 bits or 16 bits or whatever. That's the resolution. So immediately at the very source, we will probably introduce some impairments right at the source as we convert an analog signal to a digital signal. And so that is an important parameter because some of that impairment cannot be removed because you've introduced it right at the source. And that has to be then later reconverted back to its original analog form. And of course, there's something called quantization, and that's a concept in sampling that inherently introduces some amount of noise. That's called quantization noise, and that depends on how many bits you use. So that's one of the things that happens right there at the very beginning because of the conversion process. These days, most all signals are converted to digital because we've learned that that's a more efficient way of transmitting information. I think the word bits, binary information digits, I think they used the last letter there. It was invented sometime in the 20th century, early 20th century, and that was used to transmit information, convert analog signals to bits, and pack them and transmit them, either with some various technologies. So now, in addition, we have to transport these bits of information. And there we've developed a whole slew of technologies. Originally, maybe let's say 30, 40 years ago, we were using frequency division techniques where we modified the analog signal in some fashion to be able to transmit it over long distances using electromagnetic waves. But we learned that perhaps transmitting bits of information using the same technique is more efficient because all you have to do is distinguish between ones and zeros rather than trying to distinguish the entire waveform. And so that process of converting the analog signal to bits is a much more efficient way of transmitting information because your decision making is much more simpler. And so as the network was built around this digital transmission, initially, let's say 20, 30 years ago, most of the network was digital, and it was called an asynchronous digital hierarchy based on we've entered the digital age where analog and inherently digital signals are being converted to bits of information and being transported by some modulation scheme, efficient modulation schemes that allow you to transmit over air, space, fiber. Of course, fiber is very efficient. You can transmit extremely high rates previously, but the legacy network still uses copper and cable that uses electromagnetic waves, although fiber is also using electromagnetic waves, but it's more electrical signals versus optical signals. So different end of the spectrum there. And now, the type of impairments that these networks introduce essentially has to do with the type of signals that are being transmitted and the way that they are being transmitted. If it's analog signals, well, the defining characteristic of analog signals is they are continuous and they have to be digitized. So inherently at the very beginning, you introduce quantization noise. And since they have to be perhaps amplified over copper or cable, there is this electrical waves that introduce heat dissipation and amplifiers and all of that. So that introduces this additional amount of noise, and you have to worry about that. And if you're transmitting these things over large distances, like via satellite, you have to you will introduce lots of attenuation and also noise, and you have to overcome those by a repetition process. In the case of satellite, of course, it's extreme because you have to reach the satellite before it gets repeated. Other forms of distortion because of this amplification is you get phase distortion and attenuation distortion. In a telecom network, you get this other form of distortion called echo, because we're trying to send signals in both directions at the same time over media like, for example, two wires. And that simultaneous form of transmission introduces a phenomena called echo. Now, we won't get into that too detailed, but echo exists because of analog networks. Now, these days, echo exists because we are using speakerphones. So there's inherently the feedback from the speaker to the microphone. So echo is still with us, even though we have essentially four-wire networks. So that is essentially the sort of the scheme that we're in, and this is where different types of impairments are introduced. Okay. So again, the same viewpoint, except that now we've got one of the advantages of packet is that this access is through a uniform interface, and we talked about that last month. All you have is one interface, an Ethernet interface, whereas with legacy TDM technology, you're dealing with a multiplicity of interfaces. You have an interface for voice, telephone, for example, two-wire. You have an interface for data, and that used to be things like RS-232, RS-449. You have dedicated video networks, and originally they were transmitted using cable and satellite using analog technology. So they were separate from the telecom network. And data was adapted to these networks by using, by converting the digital signal to a voice band signal using modems. So it was a variety of interfaces that were used for each specific type of traffic. And that has since, or we're in the evolution now of converting everything to this uniform interface of Ethernet. But legacy networks still exist, and we still have to deal with it in this transition from TDM networks to legacy. One other thing that I think we have to worry about is that there was a lot of investment put into the infrastructure, and that investment is essentially what we call SONET, that's a synchronous optical network, and synchronous digital hierarchy. So this technology is embedded in the network, and in fact, it is the predominant form of transmission. And it is it's based on fiber, but it is based on a TDM technology. Now, slowly that technology is being converted to a direct Ethernet carrier technology, but that's going to take some time. So most of the packet network, or TDM, or wireless, is based on this SONET SDH technology, which is fundamentally a time division technology. And there, we're using fiber as a raw transmission medium, and in geographically distributed areas, we might be using microwave and satellite and wireless techniques. So there's a hybrid network involved, but the core network is this SONET technology, and we use something called packet over SONET for transmission of packets over SONET. Otherwise, the conventional TDM and analog signals continue to traverse this SONET core network. And the type of errors that are introduced is what we will now look at. Okay, so we talked about what kind of errors are introduced in Ethernet in the packet world. That is also based on the SONET technology, because fundamentally the fiber technology is the underlying transmission scheme, but fiber tends to be very error-free. So the error mechanism is really is not really transmission-based, but it's really based on the mode of transmission. For packet, it tends to be packets being dropped or lost or resequenced. So it's actually a self-inflicted impairment in the manner in which we send that. It's not governed by noise, for example, at least not when you're sending packets in the core of the network. It's more in the mode that we select to transmit information because of the packet mode. Now, similarly, when we're sending information in this TDM format, which is what we've been doing up until this advent of packet, we are taking analog signals, converting them to digital, and then streaming that in a time division multiplex manner. So it is streamed continuously rather than in discrete packets. So this introduces a different form of impairment. And the kind of impairment that we're talking about here is more related to the multiplexing of the signals into this hierarchy. Initially, it used to be this T1, E1, T3, OC3, STM1 technology, which was it's called a plesiochronous because there was not one clocking scheme governing the entire network. T1s could have their own clock. T3s and E3s had a slightly accommodated this timing variation by adding more this information called stuffing bits, and it used to accommodate this timing variation by a means of what's called stuffing and destuffing. So this is a process for multiplexing, and so this is where, again, these errors that we are now introducing are, again, self-inflicted errors because the equipment is the predominant source of errors or the method of multiplexing. So now we have errors introduced because of timing and not so much by transmission, though, because transmission, the fundamental thing is signal to noise, but over fiber, signal to noise is excellent. So you essentially have error-free transmission. But because of these timing variations of different services and these multiplexing errors that propagate through the multiplex hierarchy, you get different manifestations of errors. And these errors are like jitter because of this stuffing and destuffing. Those cause errors, bit errors, and frame errors, and these are propagated through the digital hierarchy. So it's a different kind of an error environment. It's not your usual types of errors associated with signal to noise, which is what the older methods of transmission, either FDM or analog transmission, was prone to. These days, these errors are more or less as a function of the switching, the transmission, the method of multiplexing. So that, in a sense, is sort of gives you a little picture of the kinds of impairments that we're talking about in general. Essentially, there are self-inflicted impairments because of the way we tend to transmit information, either in the TDM world or in the packet world. It's the way we packetize, the way we route packets. Because of those methods, we have impairments due to those modes of transmission. Okay. Okay. So let's just quickly go through some of the different media that is available in these hybrid networks, and let's just talk about that very quickly, and then we'll get into some practical, since we've lost a little bit of time here, we'll get into some practical applications of introducing impairments, and we'll try to cover analog because that's the least understood form of impairment, so we'll cover that quickly. But first, let me just quickly go through these impairments for different media types. Satellite. I think you all know about satellites. They have a very long delay because of the fact that the geosynchronous satellite is 36,000 kilometers high in the sky, and it takes time for the electromagnetic waves to propagate and repeat and propagate back down. So there you're talking about the conventional form of impairments, because it is governed by signal to noise ratios. The signal has to be transmitted a great distance. It suffers through distortions and attenuation, and then gets repeated. So you are actually having your basic form of impairment there, governed by signal to noise. But of course, you have the large delay associated with satellite transmission, and you also, these satellites tend to drift, and so that gives you a little bit of what they call wander or jitter due to the slight wobbling of the satellite in its orbit. Okay. So those are the so it's a very large delay, and for voice transmission and data, it's you have to account for these large delays through the protocols that you use, either for voice. Of course, voice, you can't do much about it other than to wait. You can get rid of the echo, but you cannot get rid of the delay. So you will get those unavoidable impairments of double talk or talking on top of each other. Okay. Microwave impairments. So microwave is still used, obviously, in geographic diversity where we don't have inner city fiber transmission end to end. And there you're talking about line of sight, point-to-point connectivity, and those types of engineering things. These types of networks, satellite or microwave, are easy to deploy because you don't have the whole infrastructure of laying cable and so on. But they have the problems of your fundamental signals and noise limitations. You have to repeat the signals after a certain amount of distance, and they'll be subject to rain and snow, or in the case of satellite, sun outages or something like that. So those are again, in these forms of transmission, you are limited by bandwidth and the availability of electromagnetic spectrum, and so there's all sorts of interference. So there again, you're talking about classic forms of impairment, co-channel interference or adjacent channel interference, noise, and so on. Different from fiber, right? Fiber impairment, we talked about this. It's fiber is godsend. It allows you to transmit information literally thousands of kilometers before repetition. You can some fiber that's being laid recently, I know, can be laid without any repetition whatsoever in the Pacific Basin, for example. That's an incredible feat. You can get extremely high data rates, terabits per second, so and virtually error-free. Now, of course, when you transmit such high-density information over single or a few fibers, you're prone to, of course, you're vulnerable to outages or fiber cuts, or these are very common. So you have to worry about that, and you have to have redundant and diverse transmission. In our office here, for example, we worry. We have high-speed interface, high-speed Ethernet based on fiber transmission, but we have to worry about outages. And so we have 2 or 3 carriers that are used to ensure that we can have operation 24/7. So that's the copper cable. I think I talked about this a little bit. Fundamentally, you're talking about electrical wave propagation, and therefore you have high power heat dissipation. You have attenuation. Again, this is a classic form of transmission, which is subject to signal to noise and those types of things. Conversion, it's easy because conversion of traffic, whether it's voice or video or whatever, to an electrical form is relatively simple. It's been known for hundreds of years and how to do that, or 100 years, by concepts called modulation and so on. But there again, because of the fact that it is an electrical wave, you're dealing with heat dissipation, and you have to deal with amplification. That means you have to deal with noise environments and so on. So that introduces your classic forms of distortion called frequency and phase distortion. And you have much, much higher bit error rates versus optical fiber. Okay. All right. So that is sort of sets the stage, and I apologize for that long-winded little introduction. But I mean, what it comes down to is that we have to have platforms with all of these multiplicity of interfaces for legacy transmission. Okay, so you need a datacom interface. So this is the hardware that GL offers. It's a variety of hardware across all kinds of interfaces for legacy TDM and analog transmission. We talked about packet last month, but here we're going to be talking about the Sonnet and T1, E1s, and T3s. So we have all of these products that allow you these different interfaces. It's something that you have to deal with because of the legacy networks. As you can see here, we have these datacom interfaces. If any of you are old enough to know about RS-232, 420, etc., these are your classic ways of transmitting data over voice band networks using modems. So that's still used, it's still there, it's slowly being converted, but it's going to take time. Okay, so these are the platforms that we use to be able to introduce the kinds of errors that I was talking about earlier. And we're going to talk, okay, and we have these platforms where you can actually create this network environment very quickly. You can place one of these types of networks, whether it's T1, E1, or analog, or T3, E3, or even Sonnet. So we'll talk a little bit about this in just a few minutes. It's a convenient way of emulating a network. If you have these emulators running 24/7, you can easily connect into them and get this capability. Okay, all right. So let's go into a little bit of this analog impairment and that theory, and then we'll show you a little demonstration of how we actually implement analog impairments by going to a little demonstration that we have set up in the lab. So, okay, analog impairments, let's review very quickly. We're talking about analog signals. That means we're sinusoidal signals or speech waveforms, which are composed of sinusoidal waveforms. Typically, like for example, here we've got voice or a tone. It will encounter delay, the kinds of delay that I talked about. It will encounter attenuation because analog signals, when they're transmitted in analog form, will suffer attenuation if they're transmitted by through any form of electrical wave propagation. And they will be band limited, and they will encounter, through amplification process, some sort of a distortion, which was either bandwidth, frequency distortion, or phase distortion. So these are the, and So all of these introduce various forms of noise. Here, there should have been a noise addition here. So all of these. So we'll give you a little demonstration of this, how we do this. Fundamentally, you have to be able to simulate analog signals of differing bandwidths. So we'll explain that. Now, give me a moment here to show you a live demonstration. Okay, go ahead. And go here, right? Right, okay. Do you all see this? Matt, do you see this? So, and we'll put up on YouTube, you'll be able to see this. We'll show you that fundamentally you'll have to be this is a demonstration of one of our products that allows you an analog interface and allows you to transmit different forms of signals at different frequencies and introduce these impairments of delay, frequency distortion, and so on. Okay, so let me initially let's focus in on this. This is just a simple little. By the way, all of this capability is available to you in a GUI format like this, which is visually appealing, but it is also available to you through a command line or a scripted fashion. And that makes it convenient for automation and to be able to generate this type of impairments or echo or noise, etc., through that scripting language. So here, this GUI allows you to transmit tones into time slots. You can see here, you can go from anywhere from time slot 0 to time slot 23. You can select as many as you like, okay? So this is a way of transmitting this type of information. Of course, you can do all sorts of other things in terms of, you can sweep the frequency and so on. Now, this allows you a form of emulating analog signals. It could have been a voice file as well. And that is then transmitted, and you want a method of delaying it, distorting it, attenuating it, and or amplifying it. Now, this somewhat complicated looking GUI allows you to do that. And it is available in a scripted fashion, but it allows you to receive the signal, introduce a delay of some number of milliseconds, even as much as a satellite delay, allows you to introduce attenuation, and also allows you to introduce a filter. A filter is our general purpose term for introducing frequency and amplitude distortion. Now, these signals can be dealt with at various bandwidths from 8 kilohertz all the way to 16 kilohertz, and at various resolutions from mu law, A law to 16-bit linear. So it gives you a very wide range of resolution as well as sampling frequency. So a majority of the signals, voice signals, for example, you can deal with in that range. And it allows you, the same GUI allows you to take that signal, mix speech with it, or add noise to it. Here we're adding, if you focus in on this, we're adding noise, just Gaussian noise as it's called, which is essentially flat noise with no shape to it. And we're introducing it at minus 20 dBm into this tone that we were transmitting. And we're just doing that continuously. And then we're sending that back out, okay? So this is what this application, this simple application in GUI form looks like. You also have this in scripted mode. Now, once you introduce this impairment, originally the signal looked like this. If you take a look, it was a tone of minus 10 dBm. And all analog signals will have this type of these type of metrics. If it's a tone, of course, there will be a tone power to it. If it's voice, of course, it'll have a spread In this case, this is a voice signal, so it has a signal that is approximately 4,000 hertz wide. And there's a frequency to it, if it is discernible. There's a noise power, a baseline noise power, and there's a signal to noise if that's appropriate. In this case, it's a tone, so there is a signal 39 dB signal to noise. These are typical metrics for analog waveforms. Here, that we introduce this tone, you can do that either in standard MULAW, ALAW type of formats, or you can use other higher resolution formats like 16-bit, 13-bit, 14-bit, and so on. So a variety, there's ALAW and MULAW. These are conventional codecs that are used. As I had mentioned earlier, most analog signals at some point for easy transport are converted to digital. And this is the way it's done. Okay, so the other okay, so that shows you that we can handle. We have an analog interface. You can inject your analog signal into our platform, and you can define it to be either MULAW or whatever resolution you want through this mechanism. Okay. Now, after you applied all of these impairments, this delay, for example, this gain or attenuation, distortion, or this frequency and phase distortion through what we call a filter, which has a phase and frequency response to it, and then this additional noise, which is sort of a simulation of the noise that would have been introduced either by accumulation through attenuation, or through long distance attenuation, or through mixing of amplifier noise, or the process of analog transmission. And so this allows you to do that, to simulate that. And so this is the way we allow you to simulate analog signals and the impairments that go about them. And the result is, and you can see here visually what that looks like, this tone, which had a very nice power level of -10, now has been attenuated by 10 dB, so it's much lower. It's at this tone was at -10, it's at -20 because of the attenuation. However, we've also, the frequency is the same. The power, the total power is respectively less by about 10 dB. The noise power, we added noise through this mechanism of -20 dBm of noise, which is a lot of noise. And so this noise floor went up from this region to a much higher region. So the signal to noise ratio has degraded substantially. So this is the method by which we are able to impair audio signals and actually visually see them. But of course, it's not necessary to observe them visually when you're doing when you're running experiments and you're trying to assess the performance of things like, for example, whether it's modem signals or voice signals. These are the kind of impairments that you might do if you were sending, for example, voice signals through a digital medium using ISDN signaling, whatever. The data channel, right, would be subject to errors, bit errors. The voice would be subject to this kind of impairment, and you would get the resultant either lower VQT score or impairment in the signaling channel, which would not allow you to even make a call. So these are the kinds of impairments that allow you. These are analog impairments. We'll show you how we do this in the digital domain as well. But if you are interested in doing analog many times these things come up where you have to emulate, for example, a C message filter or a voice grade line that has a certain characteristic. If you're familiar with some of those ITU recommendations that specify voice grade lines, this is the way you would actually emulate very precisely those characteristics. Okay, so I wanted to show you that. And now, okay, let's go back to our presentation. And okay, we're back here now. Okay, so that same thing that I was showing could be used to also introduce line echo and acoustic echo, and evaluate, for example, echo cancelers, the performance of echo cancelers, performance of acoustic echo cancelers, or line echo cancelers, and so on. So these are the, at least even in these new networks, acoustic echo or acoustic echo cancellation is very important because people tend to use speakerphones, and this feedback is definitely there, and you do need the ability to cancel acoustic echo, and usually that's there in either the handset, the mobile handset, or it's in the desktop phone that provides that capability. So you still cannot get away from analog impairments, even though we're perhaps in the packet world, high technology world. Okay, so let's now. Okay, this is again the same thing as this is another view of the same thing, allowing you to do attenuation and of analog impairments. So now let's, I think we're actually getting to the end of our time here, but I'll quickly go to the digital digital error that we have. Okay, so, all right, and similarly, in the digital domain, we have capability both at the T1, T3, Sonnet, and other higher layers of hierarchy, the ability to introduce errors in the manner that they tend to occur in the networks. Those types of errors that I talked about that are the result of multiplexing or jitter or timing variations, or errors that get propagated because of equipment malfunctioning or losing synchronization or losing timing. These are all essentially self-inflicted errors. They just happen to be part of the way that we transmit information in an almost error-free fiber optic environment. Although, okay, if we're transmitting microwave satellite, they do enter the picture. Okay, so the kinds of errors that we're talking about is in the T1 domain, and they have a certain analog. I mean, there's a comparative, comparable types of errors in T3 world or in the Sonnet OC3 STEM1 world. So, but this is just to give you a flavor. The same thing can be done at those other interfaces. We're talking about things, when we're sending T1, E1 signals, we're generally talking about a copper environment, at least until it hits the fiber. And there, you're talking about electrical wave transmission. So you're subject to the kinds of problems when you're sending signals through electrical means. One of them is bipolar violations. And the types of errors that you would get is these logic errors associated with detecting bits or losing bits or or not detecting the bits correctly. In fact, the CRC errors is another form of errors that are indications that there are other forms of errors in the system. And the type of errors you want to be able, the range of errors you want to be able to simulate is the range that you would expect in the real world. And we provide those types of parameters, logic errors from 10 to the minus 2 to 10 to the minus 9, and so on. So FDL errors and so on. So these are this type of technique that can be applied to time slots or across the entire T1 pipe can be introduced, and well, we provide that capability. We'll have a video that shows you the following. It shows you that if you're sending, for example, in the legacy world, voice using ISDN is typical, you'd be sending MULA or ALAW voice on time slots, which would be subject to errors because of the errors that I talked about. And similarly, the data channel, the D channel, is subject to the digital errors as well. So at a certain point, these errors will be either tolerable or intolerable, depending on the rate at which you are getting these things, and that will determine your quality of service. So we have a little demonstration where we show you that as we increase the error rate, the signaling channel or the voice becomes corrupted, the VQT score gets lower, the signaling channel starts to burp, and at some point it becomes unusable, and so on. So the rates at which these things happen is kind of interesting, and this determines your grade of service for the traffic that you are trying to transport in these networks. Similarly, the same can be applied to other traffic types, whether it's data, for example, like I just mentioned, data in terms of the ISDN D channel, or it could be data if you're transmitting packets using packet technology, but you're still fundamentally using the TDM transmission for sending those packets, or you are sending fax, for example. It's a form of traffic that or images that are subject to errors, but they manifest themselves in different ways because of the manner in which the encoding takes place. So you might miss lines on a fax page, or you might miss a page altogether, or so on, or you might have to get retransmissions and so on. So these are the kinds of if you are sending data that requires very high integrity, well, you will get retransmissions, which will cut into your throughput. So that we have some videos that show you how that can be demonstrated and how you can model those things with this type of this type of simulation. Okay. Matt, shall I keep going? Okay, so here is a visual. I wanted to show you this at least. You guys can stop me anytime you want if you have any time constraints. But similar to that analog GUI that I showed you of introducing errors in the analog domain, we have this one application that is GUI that allows you to introduce errors of various kinds in some sequence like this that allows you errors of different types and different time slots or the whole pipe, allows you to introduce delay, allows you to introduce errors of a fixed nature, random nature, or other distributions, and allows you to put specific kinds of errors. And the reason for these specific kinds of errors, again, is because what I said, the kind of impairments that we inflict on ourselves because of the mode of transmission, like these synchronization errors or these frame errors, and so on, that are the result really of this multiplexing anomalies. Even though the fiber transmission is crystal clear. So this is one of those things. Again, we provide this in a CLI or a scripted fashion so that you can automate these things. So
Sure.
one of the things that I had mentioned is one of the unique kinds of impairments that happen in digital networks is fundamentally you're transmitting bits, and that means that bits have to be decoded, and the demarcation of bits, the start and stop of a bit, gets somewhat distorted as it is transmitted through the system and detected and retransmitted and so on. And this is called either jitter or wander or those kinds. Those are the terms that are used. And it's a very interesting phenomena that arises in digital transmission networks because of the manner in which we send bits. And we have the ability to do this jitter generation and jitter measurement. And so it's a very important thing, especially when you are transmitting from one transmitter to a receiver in like a central office environment where you are sending it electrically and you have some distance limitations. Many times a lot of errors are introduced right then and there. And so these types of transmitter receiver problems can be understood using this mechanism. We have, okay, so this is just again saying, telling you about bulk delay. I think I talked about this a little bit. Okay, so here's another application that we have. As I said earlier, data was transmitted before the packet world, before the advent of all this Ethernet technology. Data was sent uniquely using a technique called data link control, or high-level data link control, or using flags. It's actually a great invention. Being able to transmit any form of data transparently using flags as the demarcation, and being able to distinguish between flags and simulated flags and so on. So it's a very it's a subject unto itself, but you can read about it on our website or look at some of our equipment. But those introduce their own kinds of impairments because people tend to implement this HDLC frame data transmission technique incorrectly. And they tend to, because it is a very precise method of sending data, encapsulating data and sending it, and then retransmit. There's a whole integrity mechanism for transmitting frames of information. And so because those can have their own unique impairments, we have this thing called the HDLC link impairment utility, which can run at very high rates, at low rates, and the popular impairment software that we provide at different layers of this hierarchy. Okay, so this is again talking about the same thing, HDLC data. Now this data transmission is very popular, still exists, used widely, flags, CRCs, and this type. The same type of thing has been adopted in the Ethernet world as well, and it has a lot of similarity, but for the data world, it was used almost exclusively for almost all forms of transmission at one time or another. And it is still widely used out there, and that's an important data impairment or data impairment software that allows you to emulate or simulate these types of environments. So we have a bunch of these. Let me kind of step through this. So we have this thing available in a variety of environments, all of these different modes. Okay, let me try to go through some. We have this. Some of this impairment is available on T3, E3s, and so I'll just go through some of these slides very quickly. But the idea is the same as I elaborated earlier on in the T1, E1 realm. So when we one of the other new technologies that was introduced after T1, E1, and T3s and E3s and so on is the SONET. We talked about that a little bit, which is actually the predominant fundamental mode of transmission in the core of the network. That was a great development because it was based on synchronous technology, one timing source. So that actually removed or alleviates much of the problems associated with timing variation, and that's what gives you this crystal clear transmission capability. But still, the mode of transmission can still be impaired. So we have this equipment that allows you to transmit and receive and emulate and impair at these rates, which are associated with the SONET SDH hierarchy. These are just some of these platforms. And if you get into these slides, if you get an opportunity to look at these slides, you'll see that this technology can be used and is used predominantly in this unchannelized method, where the technology is used to send packet over SONET. In fact, I would suspect that the majority of packet transmission in the world today is in this unchannelized SONET or SDH mode, packet over SONET. That's okay. So anyway, this is again more of the SONET stuff. I think I'll stop it there. A lot of it will be somewhat repetitive, but this will be available on our website. You can take a look at it and ask questions to us later, and we'll be happy to try to answer those.
The best way to get a hold of us at GL is a simple email address. It's info@gl.com. So I would encourage you, if you have any additional questions, follow up, anything at all, email us at info@gl.com. You may want to just reference the webinar so that it'll get to the right people there. But info@gl.com is fine. Okay, so if any questions do arise while you're reviewing them, please reach out to us at info@gl.com. It's the best way to do it. But other than that, thank you. We will be having another webinar next month, of course, probably toward the end of September. And I believe, Sanjeev, that's going to be on like 5G networks. Is that correct?
Yeah, we'll plan to do that.
We're planning to do a network on the new 5G wireless networks and so forth. So it should be interesting. Okay, well, with that said, thank you everyone for attending, and we will see you next month. Thank you. Bye.
Thank you, Vijay. Thank you, Matt.
Okay, thank you, Sanjeev. Yeah.